I will tell you something about very old topic, light scattering by small particles. But you will see that old topics sometimes can exhibit very unusual and exciting features. I'm not, this is, by the way, this is my university, and I'm not a technologist, I'm a physicist, so I will not tell you about a new technology or new technologies. I will tell you about physical grounds for new technologies. And also, very briefly, because I have just 20 minutes to discuss the results obtained during the last, say, 20 years in my lab. So outline, I will tell you something, I remind you something about Rayleigh scattering, and then we will see that there is a range of parameters where, despite the particles are small, the scattering has nothing in common with the conventional Rayleigh case, and we discovered this effect, and we call it anomalous scattering. We will discuss a little bit about it. Then we discussed about scattering by high-index dielectric particles, specifically tunable scattering diagrams and giant field concentration, so-called funnel effect. Then we consider briefly dynamic effects, and then conclusions, main publications, and funding. So light scattering by a sphere. This is a very old problem, and the first solution was obtained by Lorentz even before Maxwell completed his derivation of his equations. But it was a mathematical solution. Physics is a science which deal with material parameters. And nowadays we have parameters, we have materials with very unusual parameters, which were unknown in the last century. And these new parameters actually exhibit, the old solution under the values of these parameters exhibit new physical effects. And what I'm talking about is these new physical effects. They are very demanded in nanotechnologies, in various nanotechnologies, because there are two main questions for in any nanotechnology: how to make everything smaller. If we are operating with light, how to overcome the so-called diffraction limit, and the connected question: how to tailor and control the radiation pattern at a sub-wavelength scale. So let us start with the Rayleigh scattering. This is a well-known expression for the cross-section of scattering by a small particle, by a small sphere, known as a Rayleigh formula. This quantity X is the dimensionless size of the particle, or if you like, the dimensionless frequency of the incident light. And because of this power, X to 4, we enjoy blue sky and scarlet sunset. So this equation is was verified numerous times in various experiments, and it is absolutely correct. But let us look at the denominator. I remind you that the physical meaning of the scattering cross-section. This is a quantity which describes the efficiency of scattering, and it is defined as the ratio of the power scattered in all directions to the intensity of the incident wave. So the larger the cross-section, the more efficient is the scattering. So we will see that if epsilon in the denominator equals -2, we have 0 in the denominator, and we have infinitely large cross-section, which of course is nonsense. So we can remember that actually epsilon is a complex quantity. It has an imaginary part which is responsible for the dissipative processes. Because in nature, always we have some dissipation, so epsilon double prime always is not 0, and then the denominator never vanishes. But it doesn't help much, because if epsilon double prime is very small, then close to -2, when the imaginary part is close to -2, we still have a very small quantity in the denominator, and then a particle with the size of a couple nanometers can have a scattering cross-section of a square kilometer, which of course also is nonsense. So the same effect occurs in other multiple. This is for dipole scattering. There are other multiple, such as quadruple, octuple, and so on scattering. And the same effect occurs when epsilon equals this quantity, where L is the number of the multipolarity. We have the divergence at the denominator. So something is wrong with the Rayleigh formula. What is wrong? The wrong is that the wrong conclusion we arrived at occurs because we did not took into account that a small particle is a cavity, a resonator. It has its own eigen frequencies, and when we are close to this eigen frequency, we have very strong oscillation of the free electrons inside this particle, and this oscillation, of course, are accompanied by emission of electromagnetic radiation. And this results to losses even without dissipation. It is also well-known effect. It is called non-dissipative radiative damping. Usually it is very weak, but if the dissipative losses are small, then this effect becomes dominant. And then it occurs that instead of the Rayleigh expression in the denominator, we have this generalized expression. And what is important, the Rayleigh approximation occurs and always occurs erroneous if the particle is small, but the dissipation is also small. How to find this radiative damping factor? Fortunately, we have to go beyond the Rayleigh approximation and to take the same exact solution which I mentioned, which was obtained in 19th century. So if we do that, and if we make some calculation, we will find that this radiative damping is proportional to the size parameter in this high power. And this is crucial because the radiative damping, the dissipative damping related to epsilon double prime is a material constant and doesn't depend on the size of the particle. And this quantity sharply depends on the size. And this results in a completely different scattering process, which has nothing in common, as I said, with Rayleigh scattering. I will not tell about all details. I will just show you the radiative patterns, which occurs close to the dipole resonance. This is a very small particle, and you could see the enhancement of the, this is the field of the Poynting vector, actually intensity of the electromagnetic radiation in the vicinity of the particle. And you could see very strong concentration of the electromagnetic energy in a very small size. What is very important for, that is very important for numerous application. Moreover, you could see this is the center of this localized plasmon, localized eigen oscillation, which I mentioned recently. And what is important, this is this funnel you could see, we call it funnel. So this is the area which collects the radiation from the broad outlet and then convey it to a very small inlet to the immediate vicinity of the particle. And that is because we have so huge concentration of the electromagnetic energy here. So if we change the frequency of the incident light, we could see a very complicated field structure. So then varying the frequency of the incident light, we can tailor the field pattern in the vicinity of the particle in the substantially sub-wavelength scale. That is the answer of one of the questions which I posed in the beginning of my talk. So I will show you the same picture in 3 dimensions. You could see that it's even more complicated. And this is just 2 streamlines to show you the details. and the energy flow along these lines, and the color correspond to the intensity normalized of the intensity of the incident light. So you could see again huge concentration of the electromagnetic energy and very complicated circulation in the vicinity of the particle. And this is just for comparison, this is wavelengths of the incident radiation. So all this picture is substantially smaller than the wavelengths. So, okay, if so, why these particles are not widely used in industry up to now? Because unfortunately, to observe the anomalous scattering, as I stressed, the particle has to have very small dissipative losses. Unfortunately, all metals except a few, namely aluminum, potassium, and sodium, have a very strong dissipation at optical frequencies. So we cannot use them for for application related to the tailoring of the pattern, scattering patterns. As for these three metals, they are chemically aggressive and are not very convenient for applications. So then the question is if we can replace metal particles with dielectric ones. For dielectric particles, epsilon is positive and plasmonic modes are not supported. So we cannot observe this enhancement of the electromagnetic fields related to plasmonic resonances. But instead, we have polaritonic modes related to the oscillation of the polarization of the particle. And then oscillation of the dielectric polarization may be used instead of the oscillation of the free electron gas. And the displacement current may be employed instead of the conduction current. So I will consider dielectric particles with large refractive index. We will see very shortly why I need them. And the advantage is that there are low dissipative losses at the resonances, and there are plenty of materials which possess these properties. Disadvantage is that to observe resonances, we have to have relatively large particles. This is the condition for the resonance. But if we have a large refractive index, then simultaneously we can have a resonance condition fulfilled, and we have a small geometric size of the particles. So then both conditions should be could be held simultaneously, and we can use dielectric particles for the desired purpose. So what about the materials? Maybe we need very exotic materials for that. No, not at all. Just usual commercial semiconductors exhibit the desired properties. So you could see the spectrum, real and imaginary part of four semiconductors. And you could see that in the optical range, for example, gallium phosphide has practically zero dissipation and very large refractive index. So what use can be made? How can we use these particles? I briefly remind you main points of the exact Mie solutions. This solution is so-called multipolar expansion, when the scattering field is presented as the sum of dipole, quadrupole, and so on partial waves. And each partial wave in turn is splitted, it is convenient to split on the so-called electric and magnetic components. And the amplitude of these components are described by this quantity A and B, which actually collect all the information about the particular material. So the expressions are very cumbersome, and I have no intention to present them. The only thing I want to say that instead of the dimensional scattering cross-section, it is convenient to introduce the dimensionless quantity scattering efficiency, which is the same scattering cross-section normalized over the geometric cross-section of the particle. And then, according to the Mie solution, this total scattering efficiency is presented as an infinite series of partial modes. And now I will show you these partial modes for the electric permittivity not very large, when the refractive index is not so large. If so, we could see a mass of different lines, and none of them can be excited individually. What happens if we have large permittivity? If so, then we have large polarizability of particles. Then we have large resonant amplitude. It means that these resonances have large quality factor, and then narrow resonance line. And if so, weak overlap, and then we can selectively excite the desired resonant modes. This is a similar picture, but the real part of epsilon is increased 10 times. You could see nothing similar between that. And there are some scattering diagrams which are obtained at certain characteristic points. So this is the same diagrams in three-dimensional case. You could see that slightly varying the frequency of the incident wave, we can change the scattering diagram drastically. So we can tailor actually any scattering diagram which we need. Because of that, these particles could serve as multifunctional elements for subwavelength optics, which is very important for numerous applications. This is the experimental setup where we observe these scattering diagrams, and we mimic the light scattering with visible light scattering by the scattering of the electromagnetic wave in radio diapason. It gives us, it makes it possible to measure very precisely the scattering process, and we obtain extremely good coincidence of the experimental and theoretical results. Extremely good agreement. So then this is outside the scattering. What is inside if epsilon is large? If epsilon is large, we have large polarizability, large mobility of bound charges, and then at higher frequency, the electron becomes equivalent to a conductor, and then the induced field should compensate the applied field, and the field inside the particle should be zero. Is it the case? No, because we have forgotten about the resonances. And if the permittivity is large and the refractive index is large, this ratio, the wavelength of the radiation inside the particles, tends to zero, and we inevitably have the resonance condition holds. And then we have huge resonances inside the particle, and instead of zero field, we have huge field inside it. So this is the sketch of this field for a dielectric particle, and my time is elapsing, so I have no time to comment it in detail, but I just want to stress that for dielectric particle, the magnetic field is much inside. The magnetic field is much stronger than the electric field. And also we can tailor the contrast of this field, varying the frequency of the incident light. Then this is the experiment, how to measure the field inside the particle. Of course, we cannot put a sensor inside a solid particle, but we can do it inside a liquid scattering. So then we use a fluid and a liquid, and we put a sensor inside it, and again we used the radio wave diapason to mimic the light scattering, and we measured this field, and we obtained 300 times enhancement of the magnetic field inside the particle. This is the theory, this is the experiment. A few words about dynamics. If we have resonant scattering, selective excitation of resonant modes, then if these modes interfere with each other, the higher the Q factor, the more pronounced is the effect. So we have to have a higher Q factor. But if the Q factor is high, then it corresponds to a long transient to the steady state scattering. And then if we have several resonant modes excited simultaneously with different Q factor, during the transient, we can observe a field pattern which does not exist in the steady state. So then a new effect could be observed during the transient scattering, which is within the experimental range of short laser pulses now. So this is just an example. This is a scattering by a cylinder, This is a green, green curve, blue curve, is the envelope of the incident pulse. And then this is a scattering. And you could see huge spikes of the scattering radiation just behind the incident, the phase front of the incident pulse. But what is more interesting, behind the trailing phase of the incident pulse, this is the energy which is released from the particle, and it was accumulated during the previous stages of the scattering. And this is the model which we analytical model we developed, we described this process. What is interesting, this process is accompanied by the dynamical changes of the scattering diagrams, which is indicated here in this movie. And then you give the opportunity to make, I draw your attention to the fact that the scattering occurs in a very narrow solid angle. So we have a very simple nano laser, which emits the energy in the desired direction. Okay, so conclusions. The resonant light scattering by subwavelength plasmonic particles with a small dissipative rate, the non-dissipative radiative damping plays a dominant role. And in this case, the scattering is anomalous and has very little in common with the conventional Rayleigh's case. At the anomalous scattering, there is a funnel in the Poynting vector pattern. The funnel collects the incident radiation from a large inlet downstream and conveys it to the immediate proximity of the scattering particle, creating a huge concentration of the electromagnetic field in this area. The subwavelength near field pattern of the Poynting vector exhibit various types of singular points whose type and position are susceptible to the frequency of the incident wave. I didn't have time to comment this during my talk. A resonant light scattering by subwavelength high-index electric particles with a low dissipation rate may be employed to create tunable scattering diagrams, and this effect may be a basis for designing and fabricating a new type of simple and cheap multifunctional optical nanodevices. This scattering may be accompanied by a huge electromagnetic field concentration within the particle, and in turn, it could enhance numerous nonlinear effects, which I also didn't mention in my talk. Notably, the enhancement of the magnetic field in the non-magnetic particles is much larger than that for the electric field. The field pattern within the particle has a tunable contrast. The tuning is achieved by the varying of frequency of the incident wave. Interference of several higher quality factor modes may give rise to new effects existing only at non-stationary scattering. It creates some grounds to create multifunctional nano devices, which acts in a completely different manner under the binary radiation by short or long laser pulses. This is a list of main publications devoted to these two topics, which I discussed. And this is the funding. And thank you very much for your attention.